Hello, hello, and welcome to a little video about Target 1A. In Target 1A, we look at functions and non-functions, and we'll also look at domain and range. First, let's take a look at the different ways we can represent relations. One way, of course, is ordered pairs. Ordered pairs always come in an X, Y order. And of course, we have equations. You've seen those pretty often. We also have verbal relations, so something that would be a word problem. And we also have this thing called a map. Domain and range refer to the x's, or your independent variables, and y's, your dependent variables. We also have graphs and tables. You've seen these most often. On a graph, we have the picture of a relation. And in a table, we have a list of our domain and range, which are x's or y's. Now, to understand what a function is specifically, we need this definition. A function is a relation that assigns each element of the domain, which are our x's, exactly one element of the range, which is my y's. So what I would jot down about this, and just in my own words, is, oh, no, that's not what I want to write. I wanted to write x's can't, oh, I'll zoom in. It's not letting me write the way I want it. Give me just a moment. Thanks for bearing with me. X's can't repeat y's can. Every x gets exactly one y, and that's what we had in the definition. Every x domain has exactly one element of the range y, and my favorite way of remembering it is x's can't repeat, y's can. So, with that in mind, let's take a look at number 1. Is this a function? Well, if we take a look at the domain, our x's, I don't see any of them repeating. So yes, because they don't repeat. These are x's, these are y's. Oh, by the way, if you notice, our y's do repeat. We have 2 -5s, and that's totally fine. The y's can. Ooh, next we have this map. Is this a function? This is not a function because of this 4. Oop, that's the bell. All is well. But this 4 goes to 2 different pieces of the range, which means this x goes to 2 y's, and that's a big no-no. It's still a relation, just not a function. Okay, verbal. The relation between students in your school and each student's birthday. Now, every student has exactly one birthday. We're not going to count half birthdays. I mean like real, regular birthdays. The ones that would be written on a birth certificate. So this is a function because one student has one birthday. Next, let's take a look at how we would write equations to represent functions. Now, we have the scenario, U.S. shirts charging $8 per shirt, plus a one-time charge of $15 to set up the shirt design. This is how we build the problem. First, we have $8 right here. That goes here. The word per means multiplication. Let's see if I can write it all tiny. Mult. Go. Per shirt. Now, I don't know how many shirts I would like to buy, so I'm going to call it X because it's an unknown number. Then we have the word plus, which means add, which we have right here. We have an addition. And a $15 charge, a one-time $15 charge to set up the t-shirt design. We add 15 because we only have to add it once. Now, once we add how much money we spend on each shirt and figure out how many shirts we're getting, and then add it to $15, what we get is our total cost, which is right here. Y would be our total cost. Now this looks like a regular equation. This is a function because each amount of shirts that you buy, you get one specific cost. So if you buy one shirt, you pay a specific amount of money. You buy 2 shirts, specific amount of money. 3, specific amount. There's no sales, no deals, no nothing. Because of that, it's a function, and we use it, and we use function notation to write it. Now, instead of y in our original function, we are going to write this. Now let me translate it. The f parentheses x is actually f of x. That's how we pronounce it. And to go even further, that f means function. Now I'm just gonna, oh, this is working out. I was gonna abbreviate it, but I can do tiny letters. Nice. Right, so instead of just y equals, we're being super specific. We're saying, hey, this is not just an equation. This is a function of x. The reason we have it of x is because this x refers to the x in the problem. If we had 8z, we would have a z inside those parentheses. We can make these functions look a little bit more unique. And here's how. So instead of writing f of x, we could write c for cost and s for shirts. So instead of saying f of x, we have c of s, which is really cost of shirts. Now, since we changed what's inside those parentheses, we need to change what is in our problem. So instead of 8 with an x, we have 8 with an s plus 15. Whoops. Plus 15. We still have the same indication of a function right here, and we are still looking at a variable, an independent variable right here. Instead of x's, we have s's. So the only difference between this f of x equation and the c of s equation is that we made it unique to our problem. It's not some random function. It's specifically the function that has to do with the cost of shirts. Considering this function, which expression represents the domain? Now, in this function, the domain is represented by 8s plus 15, but specifically s, number of shirts. Next, let's take a look at the range. Well, if this side of the equation gives us the domain, this is our range. So C of S is our range. Really, that is the total cost. Right. Possibilities for domain and range. Now, in this situation, our domain has to do with the S's, the shirts. The smallest amount of shirts I could purchase is 0. I could just not purchase any shirts. So S, our shirt amount, has to be greater than or equal to 0. Because theoretically, I could order my design or pay for that design and then order shirts later and not get them right away. For our range is our cost. C of S. Now, in this problem, we are told that before we order any shirts, we have to pay a one-time fee of $15. So the least amount of money that we could spend is $15 because even if we don't buy any shirts, we have to pay for the design. Another way of seeing whether a function is, or I guess whether a relation is a function, is with the vertical line test. It's not that creative of a name, but what we do is quite literally draw a vertical line through a graph and hope it only passes through once. So here's a function, pass through once. Here's a non-function, it passed through twice. Now, I always recommend you do more than one line, just in case. Here's an example of why. I once had a student draw a line over here on the end of this and say, oh look, it only crosses once. And that's just not fair. Draw more than one line, just to be safe. So that's all we do if we have a graph. If we have a bunch of ordered pairs, so a bunch of points like this, x comma y, we look at the x's. Let's see if I can type this. It wasn't literally letting me type before. Oh, nope, nope, nope. We're not doing that. Not working. Look at the x's. Can't, there we go. Repeat. The x's can't repeat. Now, if we look at an equation, well, we don't have a table. We can't just look at the x's. What we're going to do is plug in independent variable and you should only get one answer. I don't know why it's not letting me type, but that's okay. Should only get one answer. Let's put these methods to use. Let's do it. Is this a function? Well, it's an equation, so we've got to plug something in. So I'm going to plug in 2. When I plug in 2, I get 9. Let's try one more, just in case. If I plug in 3, I get 27. I plug one thing in, I get one answer. This is a function. For every house, there is one and only one street address. Now, this kind of gives it away. This is a yes. What gives it away is one and only one. One house, one address. If you're thinking about apartment buildings, the building itself has an address, right? It's just the units that are more specific, right? Is this table a function? Well, let's see. Look at the x's. Do they repeat? Yes, they do. This is not a function because the x's repeat. How about this map? This map is not a function because this domain goes to 2 ranges. So this x repeats. That 2 should not have 2 arrows coming out of it. The fact that the 4 and the 6 both converge at the 9 on the range, that's fine. It's just the 2 that has 2 arrows going out of it, which makes it not a function. Ooh, set of ordered pairs. Let's look at the x's. -7, -5, +2, +3. They are all different. This is a function. Ooh, perfect. We get to use our vertical line test. Let's do it. I'm going to draw a vertical line through here. It passes through once, but just in case, let's try it over here. and it passes through once. So yes, it's a function. What I suggest to my students usually is you can also grab your ID and drag it across your page and see if that is a function or not, because your ID is a perfect straight edge, and by dragging it across the whole graph, you actually get to test out every single point on the graph and see if we cross once or twice. Okay. Now, if you want to follow along in your book, number 9 is referring to graphs on page M129. Judy has grouped these together. The question is, are they functions? Let's test it out. When I draw a line through letter D, this circle, not a function, crosses through twice. I draw one through K. Oh, let's draw another one through D just in case. Okay, still 2. I draw 2 through K, they both cross twice. And oh my goodness, not only does it cross twice, it crosses all the time. Because it is a vertical line. No failed vertical, oh man, I forgot my E. Failed vertical line test. Number 10, so if you're one of my students, we did do this in class. What we did is flip back to pages M129 through 33, and we discussed whether or not these were all functions or not using the vertical line test. I'm not going to go over them in this video. What I am going to look at is the domain and range of a function. We can look at the domain and range of a function. The verbal statement would be domain is the independent variables. And for the range, dependent variables. And you have to read the problem and see what makes sense for that specific problem to be the independent, that becomes a domain, and the dependent becomes the range. If we're looking at a graph, however, or even, a table, your domain is the set of x's, your range is your y's. Let's take a look at a graph. So here is, let's do this one right here. Whoops, I'm trying to zoom in and it's just not letting me. Okay, let's do domain and range here. So the domain is going to go for the x's. Our x's, whoops, no, not help, draw a pencil, all right? Our x's go horizontally, left to right. This is my leftmost. That is my rightmost. So we go from -7 on the left to +6 on the right. When there's an open circle, we use these symbols. When there's a closed circle, greater than or equal to. Okay, now let's take a look at the range. The range are our y's. So we want to look at the bottommost to the topmost. Now it looks like the bottommost of our y's is at -2. So -2. And the topmost, so that's bottom, and top is 8. So our range is from -2 to 8. I'd also like to talk about some intervals. Let's look at this graph. I see the graph has 3 intervals, and here they are. One interval happens right here. That interval is constant. I'm going to jot that down here. Constant. Doesn't go up, doesn't go down, and constant happens from -7 to -4. And let's highlight constant. Boop, 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 boop. Next interval goes from -4, it goes all the way up there. That one is going upwards. It's increasing. It starts at -4, and it increases all the way, what's that, +1? Yeah. We're looking at the x's, by the way, not the y's. Boop, boop. And then I see one more section here. It goes from 1 to 6. And we're going down, so we're decrease. From 1 to +6. And let's color code that as well. Boom. Okay. If you have any other questions, would like any other clarifications, please contact myself or your teacher, since this is just a supplement to your lessons. Have a wonderful rest of your day. Bye.